Go ahead. Yeah. This is chapter 6. No. Chapter 5 still.
Yeah.
And it has a lot of information. And we now at safety devices. So, guys, safety devices. So these are the 3 most common ways to protect the circuit from being burnt out or being damaged. We said that 2 things happen to a wire when current goes through it. What are those 2 things? Any? 2 things happen to the wire when you run current through it. Excellent. So magnetism and heat. So to protect the circuit, if it gets to overload from overheating, because what happens if it overheats? What's the first thing that's gonna happen? Huh? Yeah. What is the first thing that will ignite?
Probably whatever.
The insulation.
Okay.
90% of house fire is what? Electrical.
Yeah.
You put too much things on the power strip, it gets overloaded, starts to heat, the rubbery stuff around the wire catching fire, and boom, we have electrical fire. So these are 3 ways we can protect the circuit from overloading. If you buy a power strip that has surge protector, probably some of them have boxes with a fuse in it. This fuse is rated at 15 amps. Normal amperage. How many amps? Brody? How many amps in a normal circuit in a house?
15.
15. So every parallel circuit has 15 amps. If I look at this panel, every circuit has its own breaker, and each breaker is rated at 15. Which one has 20?
The air conditioning.
The kitchen.
The conditioning, the kitchen, what else?
Bathroom.
Huh? The dryer, the garage. So these because you have more equipment. So 15 amps. So if you were to buy a power strip that's supposed to protect your circuit, you have your Xbox, your DVD, Blu-ray player, your whatever, same power strip. If they were to protect that power strip, what fuse they will put in there? How many amps?
15.
15.
Really exactly 15?
Yeah. Sometimes even less. Because you don't want to exceed that. Once you exceed that, things goes bad. So 15 amps. So the fuse is an overload protection. They have a small, thin, let me show you here. Small, thin wire that is supposed to melt. It's a mix between lead and something else. It will melt once you exceed that amperage. Why? It will overheat and completely melt and break the circuit. So you can replace that. So a fuse, it's a good way, but every time you have to go and replace it. And before we evolved a lot of technique into how to make circuit breakers, we used to use fuse. When I was young, I used to go out and every time the AC just surged, the fuse would break and I have to go out and change the fuse. I've never, ever, under any circumstance, replaced the fuse with a wire.
Using wires are different.
Yeah, you can put a wire in there, it will work, but then the circuit is under severe danger, especially even in your car. So in your car is even worse because you don't want the car to overheat and you don't want something to catch on fire. If your car catches on fire, something's gotta be mostly electrical, and your car has oil, has rubbers, and has gas, so you don't want, yeah. So look at your circuit breaker, do not put a wire. So fuse, simplest way, it's very easy, it melts when it goes. Thermal overload, they're also operated by heat. They operate similarly to the thermostat. As a bimetal, once the system overheats, it will pop. You see those on motors, because we don't want to put a fuse in there, it will pop and cut off the circuit. It's another way to protect the circuit from overheat or overloading. When does overload happen? When you put too much control on the same circuit. So for example, if you have a power strip and you put so many things in it, probably have everybody in the kitchen, you have the microwave on, the oven on, the coffee maker, the toaster at the same time, boom. You'll hear a click and the power goes down. That's a circuit breaker, not a fuse. Magnetic overload is also the same thing, but this one you can always reset. So this one you can reset. How does it function? Simple. So you'll have your coil. So what did we say that happens? As Benny said, two things: electricity, when current goes through a wire, it overheats, becomes hot, and magnetism. So we put, this is a simplified way to look at it. So we have a coil. The magnetism in the coil is stronger than the wire, correct? So the coil is there. So as we draw more current, the magnet here gets stronger and stronger. If we exceed the limit to burn that circuit, this magnet will be strong enough to pull this box up and trip. And this is also loaded with a spring. So it's completely measured and calibrated so it will trip right away using this magnet. So there is no permanent magnet there. There's only a coil that will activate when we reach a certain amount of amperage. Make sense? We go back and reset it. So it's convenient because you can always go and reset it. However, if you keep tripping, you should check the circuit. Why is it tripping all the time? Something is up. If there's a motor involved, the motor could be stuck. The bearing could be stuck. Maybe you should measure your amperage draw for the equipment. Maybe you're drawing too much amperage than you're supposed to. So these are the three ways to protect your circuit. So fuses, this is what they look like. Some of them you have to replace completely. Some of them you can replace the strip inside. Make sure you check the amperage on it and the amperage draw. Otherwise, it might you might exceed the limit, and then you're not protecting the circuit. Big ones, we use those on big breakers. So if you look at these, there are slots here where you put fuses. And why do they want to put fuses, not just circuit breaker? I'll tell you why. So we have two kinds of loads. Some loads that draw a lot of magnetism, and some loads that just draw a lot of heat. We call some inductive loads, and some of them are conductive loads. Let's write that down. So inductive loads, their basic function is using magnetism. Can you give me an example of an inductive load? Is this inductive or conductive? That's inductive.
With magnet.
We're using magnetism. Correct. What else? Motor. That's magnet.
Thermostat?
Thermostat? No, it's inductive load.
Yeah.
There's no no magnet in it. There is no magnetism involved. So conductive load is like a light bulb, heater, capacitor, TV, screen. It's all based in heat. There is nothing moving in it. There is no magnetism involved to do a function. So when we put the circuit breaker here, we put fuses. We don't know what kind of load there are, but we are trying to counteract the heat in the system, so we want to burn the fuse and not just strip a wire. And also, when you have a system that has an inductive load, usually you want to put a circuit breaker, because if the motor is stuck, sometimes it will spike, and you don't want every time you spike the load to have a fuse. Spike to have it, so the inductive load to have resistance and to spike your load. So that's why we use fuse instead of circuit breaker. So two types. You might think, why do we use fuses? Then they're very stupid because we have to change them all the time. No, we need to, because some loads will not react the same way. Make sense? If you think about it, it makes sense because also in plants, in power plants, they put a fuse. Why? They want somebody to go and check what happened. So you want to go to the location and see check what happened. And also sometimes they put a fuse to identify which circuit actually burned. So you're gonna go and find a lot of fuses. So the fuse in that circuit that burned, you will minimize what you're gonna check. You're gonna check that small circuit, not the entire thing. So it's kind of a way to troubleshoot. And it seems very simple now. Our circuitry is very small, but when you go in a power plant or a big control building, it's so many circuits. It will help to know which one actually tripped and why, so you can reduce the time when you spend trying to troubleshoot the system. Okay. Questions about protecting the circuit? Fuse, induction, we don't want to overload the system. If wires overheat, that will burn and it can cause fire. Okay. Another equipment is a transformer. Is transformer inductive or conductive load?
A transformer.
Yeah.
Inductive.
Inductive load. Thank you very much. It is inductive load because there is an iron core here and there's two windings. What does a transformer do? Huh? Thank you. It increases or decreases the voltage. We saw one that increased the voltage from 120 to 15,000. That's a lot of voltage. So 15,000. So think about it as increasing the pressure of the garden hose. The pressure is constant. If you decrease the opening, the pressure will be so high it will go further. So you are playing with the pressure. This is the symbol for a transformer. This is what it looks like. So what kind of voltage do we have in HVAC for us in our 24? 120? 240? Yeah, for sparking up 10,000. So there's a lot of stepping up and down. Controls, like thermostat. This board over here. What is the voltage for control? 24. All controls are 24. That's why there is a transformer. So I'm gonna plug it to this to the wall. I'll get 24, and this board is 24. So whenever there's a transformer, this is for control. With control, we don't want a lot of voltage. Okay? Moving on. And that's the symbol, as you can see, two windings with induction between them, and it can be sometimes different. Questions? Again, if we want to find what this symbol means, we don't remember, or some industry is using different symbol, where do we check? Check the legend. There's always a map, there's always a legend on the side with all the identification. Okay. This is when things get a little bit more interesting, and this is going to be your map. Schematic diagrams. Schematic diagrams can be a little bit overwhelming.
Annoying.
No, I want to say actually some of them are annoying, especially when they put too much information in it. But depending on your level of expertise, you'll be able to navigate your way through it, just like a map. So when you go to a map, you'll find either they put just the streets and directions, And sometimes they put the buildings, sometimes they put landmarks, sometimes they put elevation, etc., depending on what kind of map you have. And if you are, for example, if you're a sailor, you have different map. If you are a construction worker, there's different map. So there's a different map, and they have different information on them. So schematic is kind of your map around the equipment. And if it gets overwhelming, try to first find where to start and find different schematics. You can ask either the manufacturer for different schematics. The installation diagram usually are very simple. The involved ones are mostly for troubleshooting. And sometimes again, if you can get a lot of things that you don't need, I'll show you how. And just concern yourself with the input and output. It will make more sense. So we have a lot of schematics. Sometimes for the installation, they tell you which each plug goes. And sometimes they put way too much information that you look into it and there's so much in the installation. So I'll show you a simple schematic diagram. So if you look at this primary control, they have printed the schematic diagram on the front. Look how simple it is. It just tells you where each wire goes. It's as simple as it gets. I'm gonna pass this around. This is as simple as it gets, and it can get simpler. If I look at this Teco zone valve, this is the simplest schematic. That's what you need for installation. You do not need to know what's inside. I do not need to know all this inside. Am I gonna weld and solder these things? No. I'm not gonna put them in. So I just need to know what's in the outside. So I'm gonna pass this to show you how not that complicated it is. So they tell you when and why the system works, and they give you symbols and lines. And again, if it gets overwhelming, you can look for another schematic. How do you find like schematics? Let's say you go to a house, you find a Beckett 115 model VW, and there's no schematics on it. It has been installed in 70s. What are you gonna do?
Look up Google.
Yeah, usually. Go to Google and put PDF, put manual, you'll find it. Simple, it is in there. If you don't find it, look at the manufacturer website. If you don't find it, you gotta consult with a friend. And by that time, you notice that all burners function the same way. A car is a car. There's an engine, there's a transmission. It can be wired or put differently, but again, the function is going to be the same. So again, you can go to Google and find the PDF or consult the manufacturer. And again, a lot of those schematics are wired, are like printed on the top. I'll show this old one, which is not the code anymore. And why do we need to know that? If it doesn't function, I want to know where each wire go. Maybe somebody wired incorrectly. Maybe some wire fell off. So I want to know where does it go. Does it make sense? It doesn't seem that complicated. They put things on it. So there's something called the pictorial diagram, also known as a labeled or line diagram. It's what you have in your cover. Very, very basic. Has the wiring. Where does the hot go? Where does the neutral go? Where does the color go? And how does it connect? There are kind of like a blueprint. What's a blueprint?
The layout of the house.
Yeah. Why is it called blueprint?
Because it looks
It used to be blue, not anymore.
printed blue.
It used to be blue, it's not anymore blue, but it's still called a blueprint. So what you have as a floor plan for the other class, it's the same thing.
Blue printer.
Yeah, there's no blueprint because they make a lot of copies of it. So component that's shown in control panel are shown outside the panel and label. And there's the factual. The factual has too many components inside. If we look in the book, so I have some. That's it. So in this total diagram, it tells you where each wire go. What do you get concerned with when you do installation? Hot and neutral. And if there are wire coming out of this, I want to know where they go. Right? So What's the input here? I'm gonna have hot and neutral. What is hot and what is neutral?
The black is hot and neutral is white.
Yeah. The other things probably they connect to other components. And we want to know which each one goes and how does it function. And again, in order for any component to function, it does not only need power. What else does it need? If I have a light bulb, can you just put power in it? Current, right?
What was the question?
If I have any component, like a motor, it needs two lines, right?
Yeah.
One is hot,
One's
one is neutral. So if you connect the hot only, and there is no neutral, it's not going to work, even though you're giving it power. So you always pay attention to the power and where does it go. Pay attention to the wire size, color coding, breakers, the fuses, how does it connect. Some things are connected in parallel, some things are connected in series, and we will look at that. So installation has not too much wiring. So if we look at this one, for example, here, this is called a ladder diagram. Why? Because look at the ladder. Line voltage,
That's a legend on it.
neutral. These are connected in series. This is a pictorial diagram or ladder diagram. It's not an installation. What you have in your hand, that's an installation diagram. How things are installed. And it looks more reasonable, even though it's a little overwhelming because you just looked at it. But if you follow the wiring on those installation diagram, it's much easier. Symbols again, that's the legends in here. So if you're gonna look at it, you're gonna look at the legend. This is what I don't want to look at. It's very
Okay.
overwhelming.
Yeah, it is.
So I don't want to look at that unless I have to, but most likely you don't need to. So don't overwhelm yourself with that. That's too much. So let's skip this thing.
Are you gonna train us to do that? Exactly like that?
No, what I'm actually concerned for you to know is installation diagrams.
Hmm.
Let me see if I have one here. And actually next week, when we do the lab, I'm gonna have you draw your own installation diagram based on what you see in front of you. So it seems in the first 5 minutes it will feel a little bit overwhelming, but once you actually start making sense out of it, it's very, very easy. So again, we start always with the line voltage and see how is the line voltage is used. So we will not look at something like that. If you notice here, why do I care to know what's in the compressor? I don't really, it does not matter. So this has too much information that I don't need. All I need from here is to know where the line voltage is going, so I need to know all these lines over here. So if I blank out all the things in the middle, all I'm concerned about is what goes into this line voltage. But don't take my word for it. We will do an installation diagram ourselves. And it will look something like what you have printed on this primary control. We'll keep it at the installation. We keep it to the basic and see how it goes. Okay, so by now we finished chapter 5, all the components. It's very, very kind of basic and simplistic, but that's all what we need. So let's do a quick review here. What's a contactor?
Relay.
Big relay.
Glorified relay. Excellent. A relay greater than 20 amps. De-energized, power off.
Yeah.
The power is off. Disconnect switch
Exactly what I said.
kills the power completely. Not to the entire assembly. Energized, power on. Factual diagram, that's the
blueprint.
blueprint. Thank you. Fuse, protection, melts when you overload. Heater,
Loads and worms. Hot. Load.
a coil that produces a lot of heat, and the purpose of it to give heat. Sometimes the heat is a byproduct that we don't want, but it's just there. And sometimes actually we want the heat, so we use that. In installation diagram, that's what I pass around. What wire goes in, what wire goes out. That's what you need. And if you get one of those messy ones, go on Google installation diagram. It will be very simple. You'll find somebody in YouTube who installed it, and they will give you the in and outs. Thank God for YouTube. You can learn anything in YouTube these days. A load, something that consumes electricity. Magnetic overload, that's a contactor that also trips. Okay? So it's a contactor, which is a relay over 20 amps, but if it overloads, it will trip.
It's operated by magnetism.
Yeah, overload, same with the starter. This is the contactor, but this also trips with overload. A motor, we know what a motor is.
What is magnetic starter again?
Huh?
What is magnetic starter?
It's the contactor. I'll show you. It's a contactor that trips as well. It's kind of like this. It's a contact, but also it will trip. You usually have the red handle, and it will just pops out. These are contactors. What does normally mean?
Normally, we're all, isn't it, de-energized?
Yes, the state when the contacts are in, when it's de-energized. That's normally. Normal is when there's no energy going through it. So normally closed, when there's no power, these contacts will be closed, like this one. So it's not energized, but they are closed. So these are normally closed. When I energize them, they might open. Normally open. If it's stayed like this, when it's de-energized, that's normally open. Pictorial diagram.
Shows where all the individual.
Yes, all the individual components, small wiring, inside wiring. Don't worry about that. What's a pole?
Poles are in the motor?
No, actually, this is different poles.
Okay,
Here, for a relay or contact, these are poles.
okay.
So it's a line of action. Pressure switch, they open and close circuit based on pressure. Push buttons,
Stop.
one time, you push it, then you can push it again if it toggles. Relay, switch, type of switch that energizes another circuit. Schematic diagram, too much information. Signal lights, indication of the light, that the subcircuit is on or off. Solenoid,
Switch.
coil that opens and closes a flow or a switch. It's a coil. Okay. Again, those things, I will talk about them a lot, but once you interact with them, you'll remember them more. And I don't care what you call them, to be honest, but these are the general terms, you know? But you just don't want to go to a warehouse and tell them and say, oh, I want the thing that goes into the first thing and the other wire. So they have some kind of name, so we should know the jargon, at least in generality, you know, it doesn't have to be very specific. You can call a contactor relay, nobody will punish you or anything. They'll understand what you say. I want a 35 relay, it's a relay. And some people have to split hairs, I don't want to split hair, but for the sake of the book, it's a relay, it does the same function. Okay, that's it, thank you, and see you.